So I'll be sharing about some guidelines for cold bent facades. I think this is a trend that we have seen recently, and there are a lot of inquiries, or there are more and more inquiries that goes to us asking, they have some concerns, or what do they do about the silicone sealants, whether be it in the structural glazing application or in the insulated glazing application. So because of this, we in Dow have decided that we probably should have some guidelines that can help designers when they are at least still in design state and just not validate whatever they have during the mock-up, or sometimes even just during the building. Cold bent design is not really new. I mean, if you look back, I think even back in 2003, you can already see some cold bent facade design. But it's already, of course, during that time, it's kind of early. There are not a lot of guidelines. This is not even covered in any standards. So the guidelines during those times is not very robust yet. Now we have a project which was way back in 2006. It's called the Interactive Headquarter. This is in the USA. So this is now a 15-year-old project. It has been there for over a decade now, actually 15 years if you want to be exact. And we haven't had any problems regarding the structural glazing sealant for this particular project. There is a research paper that was actually written for this project. So if you guys want to know more about this particular project, you can go to this ASTM journal, volume 9, number 3, and the title is Durability of Cold Bent Insulating Glass Units. So this one talks not just about the silicone, but in general, the IGU performance for cold bent facade. So you can, that is available on the ASTM website. Now with that, in that research paper, I'm just going to show like a brief summary of what they have done there. So they have this particular panel with size of 1,500 mm by 3,000 mm, and they are pulling the corner to a certain point, so that what you'll have is a cold bent panel. So some of the building designs, because of the geometry of the building, will have this kind of design. So obviously, when it comes to glass, usually glass typically are flat. Of course, you have your curved glass as well, but sometimes because of economical reason, some of the construction method that will be applied will be to just cold bend the glass. So as you can see on the third photo here, that is the shape of the glass after bending. So you can see one of the corners being bent at certain dimensions, and then they will test that panel to understand what happened to the IGU. Now, that is the study way back before that interactive building was even constructed. As I've mentioned, since we've been seeing now inquiries more and more, we have decided to develop a guideline that will actually cover this cold bent facade. Now, the guidelines that I am showing you here is more on, or is concentrated or focused on the structural sealant. The glass, of course, will be, you have to check it as well, and the other elements of your facade. But this one will focus on the structural silicone sealant that is being used for that particular cold bent facade. So our study scope, so we have a physical mock-up that we use to understand the sealant behavior. We also measure failure as a function of time. So what we have learned when it comes to cold bent facade and structural sealant glazing is that what you will see initially when you first do your cold bending, you have to put in the time factor as well, because you want to make sure that as time goes on, you will not have a problem, or you will not have any sealant failure in your facade. And then lastly, we also have run some finite element model to understand localized stresses and localized strain developed on the structural sealant because of the bending. So this is our physical mock-up. It's we use an aluminum panel. So you can see we have the three corners actually fixed, and then we have one corner that's where we're gonna do our bending. So we will actually push that corner using an indenter to simulate a bending on the panel. Now, some of you may ask, why are you using an aluminum panel and not really a glass? The only reason, or one of the reasons why we use aluminum panels, because with those extreme bending that we want to do to the panel, even before the panel reaches the bending that we want to investigate, the glass would have already broken. So we wanted to use a more ductile material. So in this case, we are using a solid aluminum panel. And the ones that you see here, so we have an actual physical mock-up, and then these are our finite element models. So this 3D drawings that you see here, those are also our models inside our FE software. So we have a mock-up of a real one, and then we also have our FE model, and we want to make sure that our finite element models represent what we see in the physical mock-up. So that's why we have both scenario. So as I was mentioning a while ago, the one of the closest material you can use uh, close to glass when it comes to modeling them in a software will be aluminum. So this is the you can see some of the data here. They have close modulus values. The Poisson's ratio is quite close as well, and the density is also close as well. For the sealant that we have used, we use our Dowsil 983. So some of you may be familiar with this product. It's our two-part structural glazing sealant. So these are the dimensions that we've used here. That's the dimension. So we have this aluminum panel first with the punch in the middle. And then there's an aluminum panel, again, 304.8 millimeter by 304.8 millimeter, that is glued to that punched aluminum panel using the structural sealant with a dimension of 26 by 9.35 mm. So the first test that we did is we want to understand first at what value will the sealant show failure. So the first test was done at a peak maximum principal strain of 123%. And then instantaneously at that principal strain, the sealant already developed or showed cracks. So we are classifying that that's already a failure. The interesting thing here is that in our finite element model, it's also at 100, around 123% that we see the same failure in the same location. So that, in other words, our finite element models are also verifying what we see in the actual physical mock-up. So we have one boundary already, 123% peak maximum principal strain, sealant failure right away. Then we have another test, which we set at 104.6% peak strain. And this one is very interesting because when we were doing the test, so as you can see from here, we have it plotted against time as well. So we have time at equals 0, and then we keep on looking at what happens to that to our sealant as time goes on. So when you pull the panel at time equals 0, the sealant will go together with the other panel. Now, as time goes on, there will be some sealant relaxation. So as you can see from here, the panel, the square 308 mm panel will tend to go straight, right? So because of that, there will be some pull on the sealant itself, and this may come a little bit as of a surprise to the designer because he was expecting that the panel itself will always follow the pull, but because of the relaxation on the sealant, there will be a little bit of flatness developed back on the panel itself. So we have plotted here a graph to show that, as you can see from here, you have almost a parabolic shape of a plot here. So at time equals 0, you have a relaxation on the sealant, and then at around 3.2, 3.3 value, the relaxation will stop. Okay, meaning it has reached that full relaxation at that point. So please be mindful of that. Now, so we still continue to observe this particular panel, this particular setup, set at 104.6%. And then what we have seen is after 70 days, there was a crack that was developed on the sealant. So that's very interesting because you would think that it will stop at some point. It actually stopped at some point, but you have to look at the durability aspect of the sealant as well. That after 70 days, that panel at that configuration, the sealant will have a crack. And as you can see, as time goes on, the crack also keeps on growing. So you have this at one day after the crack, you're looking at around just over above zero point 0.5 inches, and then as time goes on, you will have it almost 2 inches after 100 days since the initiation of the crack. So what we can also learn from this is that when sealant fails, right, cohesively, just like what we're showing here in the crack, it just does it instantaneously. Uh, it's like sliced throughout the whole sealant perimeter, sealant flank. It will be slowly developing that crack until the sealant will reach to a certain point. It will stop because it already has reached the maximum crack length. So be mindful of those behavior of the sealant. Now we have set a third test, and this one we set it. So we have two boundaries already, 123, and then we have the 104%. And now let's put something in the middle. We have set it at 118.6%, and then just after 21 hours, the sealant already developed failure. There was already a crack observed after just 21 hours. So we have these three values, and then we also have an actual value of this existing cold bent project. So we have three experimental values, and then we have another value that we will be using coming from this project. So this project is already 15 years in service, and this one has a maximum strain of 20%. So this one is a little low. It was designed conservatively during that time. So we will use all of those data. So the displacement, as you can see from here, it was modeled this way, and then there's a finite element analysis done for the panel. There was also some finite element analysis done for the sealant itself to understand the peak pressures and the peak strains developed on those elements of the facade. So having all of those, we plotted this, right? So you can see from the graph, so we have three lab cold bend tests, experimental values, and then we have one included that customer case, an actual project wherein there's no failure yet after now, it's actually 15 years now. And then we plotted a graph, and you'll have this graph here. And what you've learned from this is that if you can limit the peak strain of your sealant at 15%, and when you do your finite element analysis, you should be expecting at least 30 years durability for your cold bent facade sealant. So that is very important, right? So you don't want, because of that induced stress on your sealant, because of the bend, you don't want it to fail as long as it can, right? So for now, this is what we have. This will just keep on growing. So right now it's 15 years. This, you can probably have it more than 30 years now, as this line here just keeps on getting steeper, negative slope, right? Because right now it's just at 13 years. But what we're saying now, for now, the guidance that if you can limit at 15%, you can have at least 30 years durability on your sealant for cold bent facades. So the other is, of course, your durability as a function of peak strain. So what you need to do is to also estimate the average stress on your structural joint. So the other guideline is just to use 1 psi or 7 kPa when you are looking at the stress limit for your facade, for your sealant. Sorry, no, looking at the sealant itself. So this is a very easy manual calculation that you can do. So you can see this is the formula. Stress is equal to the force applied on that corner divided by A over 2, should be the half of the width plus half of the length minus the structural bite of the sealant times the structural bite of the sealant overall. So you'll have the average stress on your sealant in this manner. So what you need to do, you can set this sigma here already at 7 kPa, and then the force value is you just need to get that from your calculation. So if I will summarize what we have here from our design approach, you can have it in three boxes here. First off, you need to determine that force F required to bend the panel. The bend can be whatever your project requires. It can be 20 mm, 30 mm, 40, 50. Just get the force required to bend that panel. That force usually is not very big. The panel that I showed you a while ago, it was bent around 25 mm. The force they required for that 1,500 to 3,000 mm glass panel is just 300 Newton. And 300 Newton is not a very big force. Next, after that, you will be able to get a bite from this formula, and you will use that as your baseline bite for your structural sealant. That bite you will use and put it inside your FE software, your finite element software, and just make sure that you will limit your maximum principal strain to 15%. So that's it. Once you have verified all of those, then you have a structural sealant that can withstand 10, 30 years of bend based on these values here. I will be finishing my presentation with here. One key thing about this, probably Henry knows this project. This is in Sydney. I saw this during construction. I haven't seen it. I really want to see it again, but of course, pandemic is hindering us from doing that. But this is a project in Sydney where it's complete. It's been finished just very recently. But this project was this one was a project with a cold bent design. And one thing about this project is that, and I'd like to share as well, is that the key thing about any facade with any unusual or unconventional design, engagement with key parties early on is very important. So this project right now, I mean, this project, the facade contractor actually engaged us very on. Even before they got the project, they were already asking us about guidelines, what do they need to consider, and then during the design as well. I remember, so the facade contractor from this is from South Korea. I even had to, so I had meetings with their design team in the Philippines. I had meeting with their design team in Seoul, just to make sure that everything, all the checks are done, that all of both parties understand the risk that we are going to have because of this unconventional design. And then even during construction, there's constant communication, there's constant coordination to make sure that it's going to be a perfectly, or at least worry-free project in terms of that code bent design. So please engage your suppliers, the consultants, whoever, as early as possible, so that whatever design is required is already integrated very early on in your design. So with that, what we always say, let's stick together for solutions for whatever you have. All right, thanks a lot, guys. That's for the presentation today.
Gerald, I do have one question. You mentioned that there's a window of 15 years in those sealant you recommended for cold bend facade, right?
Yeah.
So part of your recommendation for your clients or the contractor, closer to that 15 years, will you recommend a maintenance uh, exercise like resealant or any, like what would you do? Like what would you
Right.
recommend to your clients?
Yes, it's a very good question, especially this again unconventional design, right? One of the things that we always say, usually when there's no issue with your sealant, don't touch it. If there's nothing wrong, don't touch it. It's good. Now, if you want to have, let's say, a maintenance, so there are some countries we're in, and it's not because of the cold bent design, but more of what do they think is necessary just to do some inspection. So let's say some countries will recommend every 10 years that they will check it. They will check the facade, not just the sealant, but every aspect of the facade. They will have a check, look at random places on the facade. There are also those wherein after, let's say, a typhoon or an earthquake or anything, there's fire, you do your inspection on your facade. So I think it's good to align on those. You can do 5 years or 10 years, just visual inspection, your maintenance inspection. And then if there are really these strong typhoons and you just want to be sure, or any, let's say, earthquake, and you just want to be sure, just have a look at it. A visual inspection can already give you a lot of clues whether your facade has some problems.
Okay. Say there is, say through that visual inspection, then you find some cracks start creeping in, right, Gerald? So are you like in the process of maintenance? Are you recommend to apply the same sealant, or
Right.
I guess it depends, or?
Yeah, you're
How
right.
does
It
it go?
depends. Yeah, it depends. I guess for in that scenario, it depends. Usually, when you have a crack like this, of course, you have to repair it. I mean, you have to remove the glass. Unfortunately, you have to remove the glass. You have to reapply the sealant. But I guess if you have seen that, you have to again relook at your design and then look at the actual condition as well, whether they align during your design stage, whether the same condition is still there, right? If there are changes, then you go back to your drawing board, go back to design, analyze it again, and just see whether you missed something or there really needs some adjustment or even a change in material in that case.
Yes. Okay. Thank you. I guess this brings to the end of our session.